Hi, this is the introductory lesson lecture for regression analysis. In this chapter 7, we are going to have the following learning objectives. We want to estimate and interpret a linear regression model. So in this first section, we are really sort of laying the groundwork for how you do a linear regression analysis. And then we're going to talk about interpreting the goodness of fit measures and conducting some tests of significance. In these two sections, we'll be figuring out which is the best model given our data. And then we're going to address some common violations of something called the OLS assumptions, and that stands for the ordinary least squares. And hopefully by the end of today, you know what that's referring to. Okay, so we're going to start out with an introductory case. This is the college scorecard. And basically there's a few bullet points here. This is coming out of your text. College costs and student debt are on the rise. Unfortunately, I think this is a crime. Students and parents struggle to find clear, reliable data on critical questions of college affordability and value. The Department of Education published a redesigned college scorecard that reports the most reliable national data on college costs and students' outcome at specific colleges. And so this is talking about Fiona Schmidt. She's a college counselor. She believes that the information from the college scorecard can help her as she advises families. And she wonders what college factors influence post-college earnings and wants answers to the following questions. If a college costs more or has a higher graduation rate, should a student expect to earn more after graduation? If a greater percentage of the students are paying down debt after college, does this somehow influence post-college earnings? And finally, does the location of a college affect post-college earnings? So to get at this, there's a sample, and this is actually coming from the collegescorecard.ed.gov. This is information from 2016, so it's starting to get a little old, but it's what's provided in our eText and on Connect. So this is information from 116 colleges, and it has the following variables. It has the name of the schools. It has the annual post-college earnings. That's the column or the variable earnings. And I believe this is intended to be interpreted as the first year earnings. Then there's the average annual cost of going to this particular college. There's the graduation rate, and it's in a percent. And notice that the percent are stated here in whole numbers. So 62% is stated as 62. And for the purposes of doing a linear regression, that is fine. So that's kind of nice because it makes it, in a sense, eliminates decimals floating around and makes things a little easier to read. Then there's also debt, and this debt is again a percentage, and it's just the percentage of students that are paying down debt at the time that this variable is collected. It must be all students who graduated from that college. Okay, and then the last one is a dummy variable. So is the college in a city, yes or no? So yes is 1 and no is 0. Okay, so using this information, the question is, how do cost, graduation percent, and debt percent and city affect earnings? So she wants to make predictions for post-college earnings using regression analysis. And then, of course, you don't just do this willy-nilly and don't care. You also need to make sure that you have some goodness of fit measures, which basically tell us if our regression model makes sense and if we can trust it, and basically, how reliable it is a good way to think about it. Determine which factors are statistically significant in explaining post-college earnings is another important result of doing this kind of work. So let's back. So that's what we are going to use as sort of our working example. But I want to just back up here and go over regression analysis in general. It's one of the most widely used techniques in predictive analytics. It captures the relationship between two or more variables, and it predicts an outcome of a target variable based on several input variables. Those input variables we call predictors. Okay, so let me get my annotation stuff going here. So right here, these input variables are what we call predictors in linear regression analysis. We make assessments and robust predictions by determining which of the relationships matter the most and which we can ignore. So that's also one of these nice things that comes out of this is you may have some predictors that end up shown that you find out don't matter. And that is information in and of itself. So we're going to formulate a mathematical model, and it's going to relate the outcome of a target variable. We call that the response variable to one or more of the input variables called the predictor variables. And we're going to use the information on the predictor variables to describe and or predict changes in the response variable. So, oops, let me clear that. The regression models are known to perform well for making predictions. Often they fail to establish a cause and effect relationship between the variables because of the non-experimental nature of most applications. A regression model may appear to search for causality, like this, the predictor cause the response, but it's really just detecting correlation. Okay, so I just want to make sure that's really clear that you you have to kind of be smart about what your variables are and think about they may not really be causing anything. They just may happen to be great predictors. So causality can be established through randomized experiments and or advanced statistical models. So in a sense, if you run a regression analysis on data and you find that there's a relationship and it really, really matters, you would then use that to design a future experiment that is a little more of an advanced statistical approach. A linear regression model postulates that the relationship between the response and the predictor is linear. Now, there are things that are nonlinear related, right? We've talked about that already, and there are nonlinear regression models. That actually is described in I believe it's chapter 8 in our book. There's some techniques where we can use all the machinery for linear regression modeling and apply it to nonlinear models. But in all of them, the target or response is denoted as Y. And the input or predictor variables are denoted as X sub 1, X sub 2, up through X sub K. And we're going to also talk about a situation where we replace these with D sub 1, D sub 2, and so on some of these. We'll talk about that in a little bit. One important new thing for you to think about or realize as we go through this is that we probably up till now, certainly for your BAI 111 and 113 classes and, other classes you've had up until now, you've probably done equations of lines, parabolas, and things like that. And those are what we call deterministic equations. What I'm going to introduce today is what's called a stochastic relationship or a statistical model. So in a deterministic equation, the response is uniquely determined by the predictors. So for example, consider the equation of a line, y equals mx plus b. If you know m and you know b, they're fixed, right? For any particular line, every time you plug in an x, you get a unique y. So this is exactly given, y is exactly given by the value of x in the parameters of the model, which are m and b. And I just want to kind of highlight here a little bit of vocabulary. For one thing, the parameters, the y-intercept and the slope, right, we call those the parameters in the model. Okay, and those uniquely determine a line. Now, what you do is you plug in an X, right? So you plug in the X and it's going to give you out an exact Y. This is how we graph a line. But you may not have ever really thought about that the slope and the y-intercept are parameters in the sense of a statistical parameter. So we are going to expand on that whole concept now. So in a stochastic relationship or a stochastic model, real life randomness and omission of relevant factors that may not be measurable can influence the response, right? So as we know, usually things are kind of, they don't always fall on a line, right? Things have noise in them. So here's two examples. So on the left-hand side, we have a deterministic relationship between X and Y. And we just have like some equation of a line and we with a slope and a y-intercept, and then we plug in X's and we get the corresponding Y's, and then we have XY coordinates that we plot and they all land on a line. Over here on the right, it's a very different scenario. We have observed X's, observed Y's coming from the same entity. You can think of it as a person. You have X's and Y's, like maybe age and weight or something. And then what we see is a trend. So what we see is it looks like the two things are related linearly, but with noise. And that's the randomness that we now want to try to understand and get at the trend underneath, if you will. So the objective of this kind of modeling is we're going to develop a mathematical model, and it's going to capture the relationship between the response variable y and the k predictor variables. And it's going to account for the randomness that is part of real life, what is referred to as the random error. We're going to start real simple because it's easier to think about things in an XY plane in 2 dimensions than it is to start thinking in 3 dimensions, or can't even really think about 4 dimensions, right? So let's start with what we call a simple linear regression model. And so the reason we call this one simple is because there's just one predictor. So the predictor is the X1 variable, all right? And it has a y-intercept and a slope, but we don't call them B and M anymore, okay? We're gonna switch over now. We're gonna rename B as beta naught, and we're gonna rename the slope as beta 1. Okay, so we take that, so we have that line. This is capturing the trend. And then we're adding epsilon. And epsilon here is the noise that we're adding to this model. So beta naught is the unknown intercept parameter for the entire population. And beta 1 is the unknown slope, or and it's a parameter for the entire population. And then the beta naught plus beta 1 times X1 is a deterministic component. So we take a deterministic component and we're going to add epsilon. So we add the stochastic component, or the random error term. And that's how, once again, as I've told you, I think on multiple occasions, usually mathematicians try to take something they understand. Well, if they take something they don't understand, they try to reduce it to something they do understand as much as possible, and try to use what they already know about the simpler situation and apply it to the more complicated situation. And that's exactly what's going to be going on here. Thankfully, it works. So the expected value of y, so all right, for a given value, x1 lies on a straight line. So the expected value, and that's, you may have covered this notation in your Stats 1, your BAI 210 class, but the E on Y just means the average. So going back to that scatter plot, what we're talking about is the trend line. And the trend line is sort of the expected value of y. And it is going to be given by just the deterministic portion up here. So, right, this is like the y equals mx plus b. This is b plus mx. We just write it in this other order. And that expected value you can think of as is the most likely value or the average. That's why it's kind of in the middle of the cloud, right? And when we look at the slope, the beta 1 is now the slope. If it's a positive linear relationship, beta 1 is going to be positive. If it's a negative linear relationship, beta 1 will be negative. And notice we're hitting the y-axis here at the beta naught. Here, again, hitting beta naught. And if beta 1 is 0 and there's no linear relationship, we would have a horizontal line that can go through the data. You could put the slope at anything you want, but in regression modeling, usually we give things that have no relationship a horizontal line, slope of 0. And that is kind of intuitively linked, if you think, with the correlation coefficient, in that when it's 0, there's also no relationship. Okay, so what I want to go through is the under the hood construction of a linear regression model. So the first thing is, given sample data with n observations of y and x1. So I'm starting just with x1, okay? Suppose the scatter plot looks like there's a linear relationship. So the goal is to find the equation of the best trend line. Excuse me. So the notation that I'm going to give here is a little different than I did a second ago, and I'm going to explain it. It's where y hat is equal to b naught plus b1 x, where the b naught and the b1 are the estimates of the beta naught and the beta 1. Okay, so remember, betas refer to the parameter. So this is the entire population. Instead, we're going to use sample data, and we're going to come up with these estimates. All right, so these are the estimates. Kind of like the X bar is an estimate of the mu, the sample mean, and S from a sample, the sample standard deviation, is an estimate of sigma. These are going to be estimates here. So here are two lines. I hope you can see it. The green line and the blue line, kind of drawn through this cloud of red dots. And the question is, how do you know? How does Excel pick it? First of all, Excel is drawing these trend lines for us. How is it picking it? How do we know which is the better fit? And the answer is, if you consider a line between a cloud of points, every single one of these lines has a distance, right? That it is from the line itself. So imagine that you are at some X value, and this is your Y value up here, right? So here's your Y value. Sorry, I shouldn't have done it like that. Let me see if I can get rid of just that. Yeah. So the Y, this point right here has an XY, and this is the value that's coming off the trend line. So the difference between this height, is what's called error. And every single point has some error. It's the distance that it is away from the trend line. Now, once in a while, you may get an actual data point that lands right on the line, and its error would be 0. But usually there's error. And the formula for the error, you can think about it, makes sense. It's just the observed yi. So that would be over here. This would be the yi. The height for that point, and this down here is an xi. So the i's just means if you have a whole bunch of them, like which one is it? Like the 456 x value goes with the 456 y value, right? And they make a coordinate pair and you graph it. And that's how you make a scatter plot. Well, each one of those y's, you subtract off the height that's coming from the trend line. Remember, this is the y hat. and it's going to equal that equation that was on the last page. Okay, and it's calculated using the B naught and the B1, which are coming, we're going to talk about how we get those. But the whole idea is once you get all these errors, we want to minimize the error, right? That's what we would think of makes sense for us as a way of getting the best fitting line. So what statisticians figured out is important is not to have the positive ones and the negative ones cancel each other out. So similarly to kind of trying to figure out standard deviation, where you take the difference from the mean and you square it. Here, we're going to have something called the error sum of squares. So we're not taking any averages, we're just adding up all the error and the error squared. So it's the sum of the squared errors is another way to say is SSE is the sum of the squared error. And so you take each one of these for every single point in your data. You're going to take the difference from what the line value, the trend line would be, and you square it. And then you add them all up. Okay. And you're like, okay, I get what you mean, but how does that help me figure out what the Y is? So let's keep going here. So this is the theory behind it. Okay. So here's the line. Here's another picture. It's the same thing that was on the last page, just kind of drawn a little different. So now we have the line Y hat, and we have the error at any point between Y and Y hat. And so we want the error, the sum of the squared error to be minimized. And the minimum is obtained. So we set all this whole thing up. And the minimum is obtained using derivatives and matrix algebra. And you can set it up symbolically and arrive at a way of finding the minimum, just like in 111, when you were finding the minimums of functions, you can find the minimum of all the possible lines that could fit, trend lines that could fit your data. And then you can find the best fitting one that minimizes that sum of squared error using derivatives within the context of something called matrix algebra. And that's more advanced technique and called gradient descent. And it's beyond the scope of our class. So we're not going to delve into it. Your friends who are taking some of these STEM classes like linear algebra, they may see something like that, but we get to skip it. Because Excel will do this for us. And this is what's called the ordinary least squares method. It's going to basically minimize the error and identifies as a result of that what's your best fit for your data, for your sample data for B0 and B1. And when you put this together, it's called the sample regression equation. Notice the word sample is in here. So it's not the overriding regression equation. It's just the sample regression equation. It has these estimates B0 and B1 in them that come from our minimizing the error to the best fitting line. Okay. The Y hat is the predicted value of the response variable given specified values of the predictor variables. The difference between those observed and predicted values, that error, the little e for error, is referred to as the residual. So each point will have a residual. Again, like I was talking about a few seconds ago, that we are going to have a difference for each between each Y height and the predicted Y hat value. A lot of times people just drop the I's and they just refer to the concept in general as the residual is Y minus Y hat. That's just kind of implied that the YI's are in there, but a lot of times people will drop it. Okay, so given your sample regression equation that we just talked about getting by the ordinary least squares method, we have the B0 and the B1. So let's just talk about interpreting those briefly. The B0, as we already know because it's just like the y-intercept has always been, it's the intercept. It is the predicted value of y hat when x1 is 0. Now, sometimes that's not meaningful. So we use the y-intercept to kind of anchor our predictions in the reality of our data, but it doesn't always make sense to interpret them directly. And as you start doing this, you'll see more what I mean by that. But what really matters the most is the B1, the slope. So the B1 is the estimate of beta 1, and it represents the change, right? Remember that the slope is the rise over run. So it's going to represent the change in y given a unit increase. So we assume that this is a 1. If this was a 1, then B1 would be just the change in y for a single unit increase in the predictor variable x1. So we call that the partial influence of x1 on y hat. And the reason we call it the partial influence is because there may be other things that influence y hat, but this is what we are focusing on and trying to get at when we include x1 as a predictor in our model. We're trying to see the influence it has on the values of y. So let's consider the college data and so if you go to Excel, and I'm sorry, if you go to Brightspace and go to the data module and download the data for linear regression examples, sorry, you'll see some data, and it is the data that's in that first example that we were talking about, the college scorecard data. Here we see earnings and cost, and let me just let me get rid of the filters so we can read these. Okay, so here's grad, debt, and city. All right, so the first thing I did is I ran some correlations. So I did correlations on everything, and really the only one I'm considering as a response variable is earnings. So I'm really just looking at what's in this first column to see what my correlation, this is a place to start. Now, later on, we may consider, because it's important to consider the relationships between other variables that are predictors. But for right now, we're primarily looking at how are the 4 predictors correlated with earnings. And I noticed that both cost and the graduation percent are both equally correlated, but I'm going to just pick on cost. We're going to start with that one. So I start out by confirming this correlation of 0.553, which we know is a moderate correlation. And I graph a scatter plot. So over here on the right, I put the cost, I copied the cost over, and I copied the earnings in the opposite order than they were here, because it's much easier to do a scatter plot if you put your x coordinate in the first, your x values in the first column and your y values in the second, and then you select both of them. And as you hopefully know by now, you can throw together a quick scatter plot, and I added a trend line. So it does look like not only are these correlated, but they're linearly correlated. So we are going to attempt to do some simple linear regression modeling on this. I've copied over what I just found from the correlation matrix. And I've copied over here the graph showing that, yes, it does look like it's linearly related. And then the proposed stochastic model is just of a straight line. We just have the beta naught plus beta 1. That's going to be our slope times the cost. And then we introduce this epsilon, which is the noise. So remember, the earnings are the y coordinates. So you can't just be on the line. That would be the red dots. You actually have to add this epsilon. So every single y has for every cost that's in the x-axis, the y is going to be, the corresponding y has also a corresponding error term. So it gets you to the red where you are on the red line, and then you're going to either add or subtract some error to get to the blue dot. Okay. And so I just put in parentheses here the notation from the previous slide, just to make sure you're tracking with me, that I've now directly, instead of saying Y, I'm calling it earnings, and directly the predictor, instead of calling it X sub 1, I'm actually referring to the variable cost as being a predictor of earnings. Okay, so just copying what was on the last slide here, but we're going to use sample data to estimate the beta naught and the beta 1. What we're hoping to make a statement about is the entire population. We want to say something not about the 116 schools in this sample. We want to say something about all colleges and universities in the United States, for example. So that's why we need beta naught and beta 1, and not just the estimates from our sample data. So we're going to use the ordinary least squares, and we're going to get values for B naught and B1 to provide that sample regression equation, or the trend line. Okay, so that's the Y hat are the red dots. Okay, so in order to do this, we're going to do it in Excel, and I want to show you how to do it. So I put that in here, but let me switch gears and go ahead and do that in Excel. So in the simple linear regression tab at the bottom, you'll find that you have cost and earnings, and these are from one sample. Okay, and then I have some other things in here we're going to talk about in a few minutes, but for right now, let's just focus on the first two columns of data, and they are really just copied over the cost and earnings that came over from the data that we were started with. I just copied those over, and I want to show you how I am getting the regression output here. So all I did to get this regression output is I went to our friendly neighborhood data analysis tool that we've been using for everything. So this time we're going to select regression, and I'm going to notice that the X and Y are kind of in opposite order. We want to put in the Y first, so that, remember, the Y is the response variable. That's what we want to have a prediction for. So in the Y range, we're going to come in here, and those are the earnings. And what I found with this tool, you do need to select not the whole column the shortcut way, but you have to actually select it down to the bottom of the last cell. And then the X axis, or sorry, the X input range is the cost. So the cost is the predictor. So I'm going to come down here and use my first sample of data. And I put that in. I have in the top cells in row 1, I have labels. The constant is not 0. So there's sometimes you want to make that y-intercept 0. We're not going to do that. And if you wanted some confidence intervals other than 95%, and you'll see that in a minute, you can put that here. I'm going to select an output range where I'd want that. And let's say I want to put that here. Then I would go ahead and run that. And I don't need to click anything else down below. I would just hit OK. And if I do that, I'll get the output that you saw there on that Excel. And that output has 3 different boxes. And we're going to go over those boxes as we go through chapter 7, and you understand what's in those boxes. And there's a lot of important information in there, but the most important information, and certainly the place to start, are the coefficients. So the coefficients are the B naught and the B1 estimates for the trend line. So the intercept is given as 28,375 and rounding to the penny to 41 cents. And the slope is 0.7168 on and on. times X1. So for us, since we're thinking of this as being a predictor for earnings, it's a y-intercept of 28,375.41 plus roughly 72 cents increase in earnings for every dollar cost increase in the cost of going to that college. So we're going to just look at that a little bit more. That intercept or baseline earnings is for graduates who went, like, if you can imagine, cost was nothing, like a free college. You could think of it as the earnings, but it doesn't really make sense to think of it that way. It's not really meaningful. You can kind of think of it more like before you start, it's kind of like your baseline earnings before you begin to attribute additional earnings due to the cost of the college. So you can kind of think of it as notice I put approximately equal to, so you can kind of think of it, if you want to have an intuitive feeling kind of, is that this is the average of the earnings data without the influence of cost. And then again, I already mentioned on the last slide that the slope is the unit cost increase. So in the predicted earnings, so the average in the population will go up by, the average earnings will go up by 72 cents for each dollar increase in cost. And we call that the partial influence of cost on earnings. All right, so let's keep going here. If a college costs, and we're going to choose some value within the range of the data, we don't want to go beyond the range of the data because we don't know if we can extrapolate. But if we looked at the range of the data, I think this is why I had those filters in here. Okay, here was the cost. Oops, let me cancel out of here. Cancel, okay. We just look at the cost in the drop down. It goes from about 10,000 to 35,000. So I'm gonna just say 30,000 per year. And then if my estimate B naught was I actually was able to hit it on the head, beta naught, and my B1 estimate, my slope, was actually the population slope. If both of those I happened to hit the nail on the head with our sample, and you know the chances of that are very small, but we'll get into that in a minute, then the earnings are going to be given by those coefficients that came out of the regression modeling, which was that ordinary least squares. That was the output in Excel. So we put those coefficients here, and when we put in 30,000 for the value, we're actually putting in the 30,000 where the X was, right? So we're substituting the cost of 30,000 here. Okay, and if we run that, we get a total of 49,881.51. So this is the Y coordinate on the trend line above the $30,000 mark. So if we were, somehow here, right there at wherever 30,000 is, and we look at the Y coordinate from this point, we find the spot on the Y, on the red dot line, and we come over here, we're going to be just below 50,000. We're at 49,881. Okay. I didn't get to build this as well as I wanted, but predictions are subject to sampling variability. So those predictions for the slope and the y-intercept, they're going to change if we use a different sample to estimate the regression. So here is the original data points are in blue, and now I created new data and new costs. So imagine getting another sample of different colleges, and we do a scatter plot and we do a trend line, and that trend line's in black. And we see that it's a different trend line. It has a different slope, has a different y-intercept. And so for the using the first sample and a cost of 30,000, my earnings were the 49,881 we were just talking about. But for the second sample, and that's in the Excel, I ran that. We have slightly different. We have a different y-intercept. It's higher. We have a lower slope, and it comes out to 48,000. So not too far off right here at the 30,000 mark, but in general, it can be pretty far off depending on what cost value you put in here. So before I keep going here, I think it might be important to just briefly remind you guys about how the structure of confidence intervals work, because that's going to start to matter for when we do, when we start thinking about various concepts within regression analysis. So recall that if you're trying to estimate a population mean, mu, using a sample, what we did is we constructed an interval around the sample mean, which we referred to as the point estimate, X bar. And we did this by having a margin of error. So again, this, if you don't remember this, go look at your BAI 210 notes or your Stats 1 notes if you took it at a different college or in high school. And you'll remind yourself that when we want the confidence interval, and we use this funny notation. So 100 times 1 minus alpha percent. So if alpha is 5% or 0.05, then this would be the 95th percent confidence level. We could say that we were 95% confident that the population mean was contained in the interval. All right, so that margin of error is X bar minus the margin error to X bar plus the margin of error. The margin of error depended on the governing probability distribution of X and the standard error in the sample. When we do not know sigma, remember this, if we didn't know sigma, which is the population standard deviation, we had to use the student's t-distribution. Otherwise, we would use the standard normal and a z-score, right? But because we are not going to assume we know sigma, we are going to be using the student's t-distribution, which means we need to know the degrees of freedom. And for a sample mean, that was an n-1. Okay. And we constructed the confidence interval as X bar minus the t quantile from the distribution times the standard error. And the standard error for a sample mean, remember, was S over the square root of n. So all of that is just to remind you stuff we've done in the past. We are now going to use an analogous approach here, and we're going to talk about the predicted value y hat. It also follows the student's t-distribution, but the degrees of freedom are different. They're the same, start out with the same n, the sample size, but this time we're going to subtract k. So before it was n-1, now it's n minus k minus 1. And that k is the number of predictor variables. So it's the number of x's, like x sub 1, x sub 2, x sub 3. For right now, we're just doing x sub 1. So what we're going to do is we're going to denote, also this is a little bit different notation. We're going to denote x sub 1 when it has an exponent of a little o. Okay, that means it's a specific value of the x1 variable. So like what we were doing a second ago, that's like the $30,000 cost. And then the expected value of the mean, we refer to that as the y naught. That means that's the y coordinate of the trend line for that 30,000. So for a given x1 naught, like the overall, the y naught was the y coordinate, or the 49,882 and 41 cents, right? And so then the expected value is what we're talking about, is so that's what the expected value of y naught bar is. And the confidence interval for that is given by that point estimate, y naught hat, Then we have the margin of error, and the margin of error is a quintile from the student's t-distribution times S, this thing right here, this standard error term, which looks a little different than what we've seen in the past. Right? This is the estimated standard error of the prediction at a specific value of the x coordinates. So that's the y naught hat, right? So that's the standard error is going to vary depending on where you are on the x-axis. So this is the estimated standard error for when you've identified the x naught. Like when we identify the 30,000, we want to know what's the standard error around that 49,000. Okay, so now I've just rewrote what was on the last slide. So here's our confidence interval formula. And I also threw up here the two samples that we have from the two different samples of data. And in the first one, when we put 30,000, this is our y naught hat. And in the second sample, we had different estimates and we still put in 30,000 and we have a different y naught hat. So I'm going to, what I'm going to do is kind of focus on sample one. And what we're hoping is that if we put a confidence interval around this, that it should capture this number, right? 95 times out of 100, okay? Because this is another sample. And so it should capture any sample. It should capture the overall sample. Okay, so let's just keep going here. So what we need in this formula is to get the standard error, the y naught hat. And like I said, it varies kind of depending on where you are on your x-axis. So the way we're going to get it is this is where you, unfortunately, this is where we have to pay the piper. So I think I've told you guys multiple times that a lot of people do this kind of work using the R programming language. And that would require that we learn R. And I decided that it was more important for you guys to learn Excel, and that Excel is used for like 99% of everything else in our class. But this is the one time I wish you guys knew R, because it's really simple if you know R, and it just does it for you, and it's under the hood in a sense. You don't have to get into the details of how to calculate this standard error of the y naught. In Excel, we're going to have to do a little workaround. So you got to have the easy out. You didn't have to learn R and all the hassle that is. Instead, you got to focus just on Excel. And but now at this point, we are going to have to do a little more work to get this standard error of the y naught hat. The way we're going to do it is we're going to add a new variable for each predictor. So what we do is we take the value that we care about for the predictors, all the different predictor values, and we take the value that was in our data and we subtract. Remember, this is a number. This is like the 30,000. So we take all the cost data, and for every value of the cost data, we subtract 30,000. We get a new column of data. And we're going to do the same thing for every other variable in our data. And if you do that, if you think about it, our new variable x1 star is the original cost minus 30,000. And then we're going to run the same regression model, but we're going to switch and run it on x1 star instead of x1. So let's just go look at Excel real quick so you can see how I set that up. So here is x1 star, and I took the cost and I subtracted 30,000. And I'm doing this and I just copy this formula down for every row in my data. And then I'm going to run a regression analysis using that instead. So I put the outputs of that down here. So here you can see X1 star, whereas here, this was the coefficient of cost was 0.71689. Here you see some values are identical, and I'll show you that. I put those side by side in a slide for you, if I can find it. Yeah, okay. So we're going to run the same regression model. And oops, let me clear my annotations. Okay. So this is where we're at. This is what we get from running X1 star. Okay. And what I want to show you is the original output. So notice all the variables in this regression statistics, which are really going to be important when we try to select the best model. None of them change by doing this. None of the values in the middle table, in the ANOVA table, change either. And when we look down here at the coefficients, the slope on cost is the same. So it's the same coefficient, 0.71687. What did change now is our y-intercept. This is what we used to have, and now we have this number. Well, look what's cool about this number, whoops, is this is the number that was our estimate, right, for the y hat. That was the y coordinate on the trend line. But now we have a different number than we have before. We had this standard error on that. And before we had this large number, 2,800. Now that number is now only 777. Okay, so what we're going to do is use this is the standard error. The reason we did all this is because we want to get our hands on that number. So the standard error on the y naught hat. So the y naught depends on what value we put in for x, which was 30,000. And that comes out to 777.67. So now we can build a 95% confidence interval of the mean prediction, so the average earnings. So if you take all the people who have paid 30,000 per year to go to college in 2016, their average earnings, and you average them, what we're going to do is put a 95% confidence interval around what those earnings would be. So that's pretty cool that we can do this with just 116 colleges worth of data, right? To do that, we're going to need to get the degrees of freedom. So it's 116 was the sample size, and that's coming out here from the observations. -1, because there's only one x coordinate in our model, one predictor, right? And then we always subtract 1 off. So we have 114 degrees of freedom. We're going to plug that 114 degrees of freedom. So in Excel, you just have it in a cell calculated, and it's going to go into the Excel function that's going to give us the quintile or the inverse when we have, and notice because it's a confidence interval and it's two-tailed in a sense, we want the middle 95%. So we want to take that 5% that's in the tails and split it between each tail. So we're going to put the amount of probability we're going to have in the tails. That's what this 2t function lets us do. We just put in the 0.05 here, and then we get the quintile in the positive on the right side of 0. We get the 1.981. So to generate the margin of error, we're going to use now that value for the t is going to go here. And we're going to use this value, right? That was here. We'll use that value for the standard error of the estimate. So if we do that, we would have 49,881.5079. So that's the y naught hat, which we can also get directly here as the y-intercept, because what we did basically when we created this variable x1 is we shifted the 0 over to 30,000. So that's why we get this number here. And then minus and plus the margin of error. So let me clean that up. All right, so we multiply those two together. And we get a value of between 48,340 and 96 cents to 51,422 and 6 cents. So that means we have a 95% confidence interval of the mean prediction that the average earnings for a cost of 30,000 per year comes out to this. So that means that what I believe is if I take 100 samples of different colleges and put in trend lines, and I estimate where the trend line is out of 100 trend lines, 95 of them will be within this range if I go up from 30,000. Okay. So this is saying, oops, I'm going to start at 30,000 and I'm going to go up and I'm going to see this. I'm going to hit the height is the y coordinate, the earnings is going to be somewhere in here, 95 out of 100 times. So if I draw this in, it's saying that all the trend lines out of 95 out of 100 of them will go through this black interval. They'll be somewhere in there. And we see these two do go through there. Okay, so now that we talked about that, there's another concept that we might care actually a little bit more about. And that is the variability in the data at 30,000. Because while it might be relevant in some situations to care about the average salary that someone would make, we might actually want to have a better idea about the average overall, but we might want to know actually what about a single specific person? Where is their salary? And to consider that where their salary might come out, you have to think about that there was a lot of variability in those dots, right? So we want to kind of come up with a range of earnings that would correspond to a specific person. And this is a new concept. It's what is referred to as the prediction interval. And it's not now we're not talking about an interval of the average earnings. We're talking about an interval for the actual individual y coordinates, the y values, the individual earnings. And it's going to have to include all the variability in the sample data. And because of that, it's always going to be wider than the confidence interval around the mean. So in this case, it's going to include the error, the epsilon from the original stochastic model. We're going to pull in how much error there was in calculating this confidence interval for any particular value. And its derivation is beyond the scope of our class. We don't need to do that. And here we see that the prediction interval, so the 95%, you can think about it, whatever, 1 minus alpha, whatever your alpha is, has the same degrees of freedom, starts out with that same point estimate as the confidence interval, the difference, and has the same t distribution and the same t quantile as we did a second ago for the confidence interval. The part that's now changed is that the standard error is this bigger amount, where we take the standard error of the y naught hat and we square it and we add to it the S sub e, which is called the standard error of the estimate. And we square that, we add those together, and then we take the square root of the whole thing. And the place where you get that standard error of the estimate is in this first box of the output from the regression analysis. And it's in there, it says standard error. That's the standard error of the estimate. Okay, so just getting down to what the prediction interval looks like and what we were trying to find. Sorry, the graph in the background here is not the one I wanted. It should be the one from the previous slide. I meant to change that. It should be this graph, but okay. The confidence, 95% confidence interval of the mean prediction is determined using everything we've done so far. And now we're going to add the standard error in here. So we have the 49,881,507 minus and plus the 1.981, the t quantile times. Now we got this whole square root thing. The 70, the standard error, y naught hat, that's going to correspond to this intercept term because we shifted everything over with the x star 1, right? So we're going to take this 77.6651 number. And I am rounding a little bit in what I put on the slide. You would do this in Excel with no rounding. So you have the full precision. You only round at the very end. Anyway, so we take that number, we square it, and then we add, and we point to this standard error number, and we square that, take the square root of the whole thing. And then what happens is that we arrive at that for a particular student paying $30,000 per year with 95% confidence, their earnings will be between $37,000 and $62,000, rough rounding to the whole thousands there. So that's, again, very powerful statement to be able to make with not too much data. Now, I showed you this very sort of elaborate way of arriving at this. You can make kind of a rough approximation. It's statistically incorrect to do it, but as long as you have only one predictor, as long as it's only a simple linear regression, you could use the, let me get my little annotation thing going again. You can use the lower and the upper 95% confidence intervals and sort of build these out to get the lower and upper bounds. It's kind of like a rough approximation. So you'd say this is the y-intercept and then 30,000 times this slope for the lower. And then this would be the y-intercept. And then this is the slope times 30,000 and get the upper bound. So those are roughly approximated. If you do that, this would come out to 37,900. So you can see it's a little bit higher than the lower end here. And this comes out to 61,800. It's just below what the true confidence interval would be. So it's just a rough approximation in case you are in a hurry and you don't have time to run a whole nother regression analysis, create a new variable, subtract off 30,000, whatever you're trying to get at. So it's not mathematically correct, but it's often used as just a rough idea. Okay, now that we've talked all about that, we're going to now expand this idea to include more predictors. And that's one of it's actually a relatively easy thing to do. It's not going to really complicate anything we've done so far. But if we include more than one predictor, it's referred to as a multiple linear regression model. And in this case, the population parameters, the slopes, how each one of those predictors is related to the response variable are unknown and must be estimated using sample data, totally analogous to what we did before. So we get the sample data, we have n observations of the response variable and each one of the predictors, up to k predictors. And we're going to use them to obtain those estimates using the ordinary least squares. And again, Excel will do this for us. So it's going to find the best fitting trend line. And we can't really visualize it because after we cross past 3 dimensions, it starts to get really hard, I think, or even impossible to think in higher dimensions. But the math is solid. So there's no conflict doing the math at higher dimensions. We just can't visualize it, but it still gives us very useful results. So we create this sample regression equation, so y hat, and it's the same thing. Like you can imagine that each one of them is a slope on that variable. So B2 is the slope on X2 in the X2 direction. If you imagine a slope in that direction, if you imagine that each one of these is pointing in a different direction, it's a slope in that direction. So it's the influence in that direction. It predicts, so then I just want to make some important, more kind of info pass information about regression modeling. Regression models have to work with numerical data. So it's going to treat everything as numerical. Specifically, the response variable has to be numerical, and that kind of limits what we can use as the response variable. But there's more advanced ways of dealing with categorical responses, but we're not going to have time to cover that in our class. But one thing you do need to know is that all predictors for sure have to be numerical. But we have a way to include categorical variables, and that is by converting them to the dummy or indicator variables like we've already been done in our data. So if you remember for channel, we had like TV 1 0 if the channel was TV. And this is just another quick little example with race. So let's say race has 4 categories. That's the variable, the column, race, and you can find in there records that either say Black, Hispanic, white, or other. You have to pick one as the reference. It's generally more stable. Your models are more stable if you pick as your reference the one that if you run a pivot table and you see which one happens the most, it's usually a good idea to make that your reference, and then the other ones are your dummy variables. So let's say I choose white as the reference. Then I would create 3 dummy variables, D1, D2, and D3. And so D1 would correspond with Black, yes or no. So if the categorical variable race had on that particular row in my data said Black, I would say D1 was 1. Otherwise, I'd say D1 is 0. And if it said Hispanic, I'd have another column of data called D2, and it would either be 1 or 0 if race was Hispanic or not, and the same thing with other. So if all of them are 0, I know that that row was white. And if you want to review this a little, you can look back on that task 2 new ARDS data, and we did that in there for channel. Okay, so that's how you deal with that. And then in the regression model, you just replace the X with a D. So you just treat it like another predictor. There's nothing else that happens. One of the things that's really nice about doing this is let's say that you were particularly interested in just the influence on a response variable of one of these. So let's say you wanted to look at Hispanic. You don't have to include the D1 variable and the D3 variable in your model. You can just put in D2, and then you would just see the influence of being Hispanic or not. So it would roll in all the information of being Black, white, or other. It would roll that all in to sort of the background or general average. And in that sense, you could just get an idea of the influence on the response variable of one value of a categorical variable. So let's go back to our original data that we started out with, which we were considering several predictors. We were considering cost. That's the one we just ran by itself. But we were also considering the graduation rate and the percentage of students carrying debt after they graduated and whether it was in a city or not. And we want to ask the question, what is the sample regression equation here if we consider 4 predictors? And then we want to interpret the slope coefficients. And then we want to predict the annual post-college earnings. If a college's average annual cost is $25,000, its graduation rate is 60%, its percentage of students paying down debt is 80%, and is located in a city. So we want to get the point estimate of, we want to get the height on the trend line, if you will, the expected value of the Y naught hat. that corresponds to all these specific values of our predictors. Okay, so we run that in Excel. This is what the output looks like, but I'm going to show you real quick how I would run it. So let's go to the multiple linear regression tab. And in here is all that data. And the way we're going to do this, again, go to data analysis. Actually, okay, and whoops, and I'm going to go to regression. And in regression, I'm going to input my range for my Y, and it's going to be my earnings, right? That's my response variable. Now notice I'm going to need to have all my predictor data in one rectangle. And we've seen this before for other things, but this is another situation where we want all that data as one rectangle. So we're going from B1 all the way down to E117. So we're going to put that in. We're going to say, yes, we have labels in the top row. We don't need any alternative confidence intervals. And we're going to pick the output range. So here I picked H2. And if we run that, we get the same table as we did before, but now there's some differences, right? Now we have new predictors here. We have some new information. So we have slope coefficients, not only for cost, but we have them for all these other predictors. Everything's going to change as a result. Everything gets shifted around, and that ordinary least squares finds the best fitting trend line through the hyperspace, multidimensional space of all these variables. Okay. One thing I did want to notice, you may say, hey, why does it say lower upper 95% and then lower upper 95.0%? So this is where if you don't choose anything, it's just going to repeat it for you. But you can get like the 90th percentile, the 98th percentile. This is where you have variability. So you can get it. It's going to by default always give you the 95% one because that's the most common. But when you fill out that little form in the data analysis regression graphical interface here, this is where if I hit a confidence interval and I change this here to 90, let's say, and then I say, okay. Now you'll see that it says lower and upper 90. So that's what I picked, okay? And a lot in my career, I haven't used anything more than upper or lower 95 except for once. So it's not very common, but you know, they wanted to put that in there. So that was nice of them. Okay, so here's the output that we just got. We have these different coefficients now. And what we're going to talk about is what is the earnings. So here's our regression, our sample. Now remember, it's a sample regression equation because these coefficients are estimates of the parameters of the real slope coefficients. If we could somehow but get our hands on all the information in the entire United States. If we were able to do that somehow, then we would have, these would represent betas, population level parameters, but right now they're estimates of these slopes. Okay, and we want to, so I'm just copying it here, and then we want to interpret the slope coefficients. So what does this mean? Well, first of all, they're all positive, so that suggests that every single one of these is a positive influence on the response. So as they go up, the response goes up. If we had any negative values in the coefficients, it would mean as one thing went up, the earnings would go down. So the way to interpret them is this is sort of the key thing to think about, that you're holding all other predictor variables constant. So you imagine that they're all like frozen, they're not moving. Then if the average annual cost, so now I'm just going to pick one cost. If it increases by $1, then on average, because again, we're referring to the trend line, so it's the average, the predicted earnings are expected to increase by that coefficient. So the earnings are going to go up by roughly 43 cents for every dollar college costs more to go to. Okay, then instead, if we hold everything constant, the average annual earnings are going to go up by $178.10 for every 1% increase in the graduation rate. Okay, now this does not mean that if you or I suddenly makes a big effort to increase our graduation rate by giving everybody A's, that their earnings are all going to go up. This again, that would imply causality, that we could cause the response to change based on changing something in a predictor. And that is not what regression analysis is doing. What regression analysis is doing is looking for correlation. So what it's saying is, okay, schools that have a higher graduation rate, the people who graduate from them have shown in the data to have higher earnings. It would take maybe a social scientist and some more work and effort to try to tease that out and see where the causality is. Okay, so the same thing is going to go with debt and city. So notice city is actually makes a big influence, right? So not so great for us, for you guys at URI, but it looks like the data suggests that people who, everything else being the same, the college costs the same graduation rate, the same number of students percentage come out with debt. If it's in a city versus being not in a city, the earnings go up by around $2,500 per year on average. So the next thing we want to do is we want to actually kind of set a cost graduation debt and get an actual average earnings. So if the predicted annual post-college earnings, this is that point estimate. This is the point that lies on the trend line for a cost of $25,000, a graduation rate of 60%, a percentage of students paying down debt that's 80% and is located in a city. We're just going to substitute into each one of the variables those values. So I just copied the earnings equation down, and I would do this in Excel. I'd be just putting in these values. And I get out of that the expected earnings, when we consider all these factors, comes out to about $45,000. Now, this model has more in it, and it's giving us a different number than what we had before. So let's remind ourselves what we had before. I'd have to kind of go through this real quick. Where were we before? So we were at closer to 50,000. Now we've taken more things into consideration. And I'm just looking at the point estimate on this sample data, same sample of data. And we were at closer to 50,000. And now when we're considering the larger model that has more predictors, we are at 45,000. Okay, so we will be looking at, well, which of those do we think is better? And that's going to be the topic of the lecture on Thursday. But I did want to just let you know that for the most part, I'm going to have you calculate the point estimates and all the extra work to do the prediction intervals is something I want you to know about conceptually and understand. I'm going to be very specific about when you have to do it. I don't expect you to do all that extra work every time. But if we did in this case, in this larger model, the prediction interval, right? So that's where you have to go in and create new variables and rerun the regression and pull out the standard error of the estimate and all that stuff. We would have a 95% prediction interval that any particular person that went to a college satisfying all these specific conditions, that they would have in earnings between 34,000 and 57,000 rounding. Okay, so that is the big lecture, if you will, and one of the reasons I am glad that this is being recorded, because this has got all the theory of doing linear regression analysis. And then what we are going to do going forward is actually just do linear regression analysis, but you need to understand what was in this lecture today to be able to make sense of things going forward. Okay, have a great day, and please answer the questions on Brightspace related to this lecture. That will give you credit for being in attending class today.